Welcome to the fourth edition of the road to, the first drawing conditions. I almost forgot. So in the previous video, we derived the first order condition of convexity for a multivariable function. For points x2 and x1, you have this relation. Now it's finally time to derive the separating hyperplane theorem, in which you have a hyperplane that separates a point in a non-empty closed convex set from a point outside of that set. But first, let's state a fact. Fact 1. The squared norm f of z is equal to the norm of z squared is a convex function. This can be proved using the definition of convexity. Hint, consider arbitrary points z1 and z2 and determine whether it satisfies the definition of convexity, where z1 and z2 are within Rn and t is a member of the interval from 0 to 1 inclusive. So it should actually satisfy this if you plug in this over here. So fact 2, given a non-empty closed convex set, C is a subset of Rn and a point x not in C, there exists a unique point y star that's in C such that y star is the argmin of all the y's in C of the norm of y minus x squared. So that's the distance between x, which is a point not in C, and y, which is a point within the boundary of C. But why is this true? And this is true because if we let y1 comma y2 be a member of C with y1 not equal to y2, and y midpoint be defined as 1/2 of y1 plus y2, what this is that say that you have y1, then you have y2. That means that this is y1 plus y2, and your midpoint is somewhere around here. So that's y midpoint is at circle. And so that midpoint must be in C due to convexity. And suppose y1 and y2 both minimize the distance from x, which is not in C, to C such that, or so that, the distance between x and y1 is equal to the distance between x and y2, which is equal to r. So therefore, x minus y sub m squared is equal to, if you do a lot of complex algebra, then it's equal to r squared minus 1/4 of y1 minus y2, 1/4 of the norm of y1 minus y2 squared. And since y1 is not equal to y2, it must be true that the norm of y1 minus y2 is greater than 0, because the norm is not 0, so it must be greater than 0. And let's see what we have over here. We have the norm of x minus y sub m squared is less than r squared. That must be true because this over here is greater, all this is greater than 0. So r squared minus something greater than 0, well, that's less than r squared. So that means that x minus y sub m, the norm of that squared, is less than r squared, which implies that the norm of x minus y sub m is less than r, if you take the square root on both sides of a positive number. Now let's move on to the separating hyperplane theorem. Let y star be the point that minimizes the norm of y minus b squared, where b is not in C and y is in C. And it's the unique minimizer of a convex square norm function. Now we may apply the first order condition of convexity. If we take this term and put it on this side, then we get this. And this must be greater than or equal to 0, because since y star is a minimizer, f of y star is the minimum. So therefore f of y must be greater than or equal to f of y star. So that means that when you subtract them, it must be greater than or equal to 0. And then over here we have, we're just restating that fact, because since this is greater than or equal to 0, if something greater than or equal to 0 is greater than or equal to something, that something must be greater than or equal to this, or 0 actually, which is what we have over here. And then since the gradient of f of y star is y star minus b, that's just the, comes from the partial derivatives of the norm squared. Yeah, that's it. So now let's x be defined as y star minus b, then x transpose times y minus y star is less than or equal to 0, and this condition is also true for all y and c. Additionally, x transpose b is equal to x transpose times y star plus x. That comes from rearranging this equation, is equal to x transpose y star plus the norm of x squared, because we distributed the x transpose to each of these terms. And that's greater than x transpose y star. And why is that true? Well, because x, or the norm of x squared, must be greater than 0. This is because, well, x is not 0, so it must be greater than 0. X is not 0 because b is not equal to y star, of course, because b is not in C, but y star is in C, which implies that x is equal to y star minus b is not equal to 0. So x is not equal to 0, therefore, well, the norm of x is greater than 0, and therefore this must be true. So thus we have x transpose y is less than or equal to x transpose y star for all y and c, and x transpose b is greater than x transpose y star. That leads to x transpose b is greater than x transpose y. And thus there exists a hyperplane with normal vector x, where x transpose z for some z is equal to alpha, where alpha is x transpose y star. That strictly separates b from c. So what is going on here? I'll show you what's going on. So you have x over here, your vector x. Then you have maybe x transpose b. Maybe your b is somewhere over here, maybe. And then you have x transpose z is equal to alpha, where alpha is x transpose y star. And maybe your y star is over here. And then your set C is over here. Y star is on the boundary of C. Then maybe you have a y someplace over here, or really anywhere on the hyperplane x transpose y over here. So what's saying is that x transpose y is less than or equal to x transpose y star, which is less than x transpose b. And if you didn't know it was a hyperplane, because maybe you're discovering this for the first time and you have no idea what, x transpose y represents geometrically, you can just say like, okay, this is a number, this is some kind of number, they're all just numbers. So we're going to draw a number line like this, and then maybe x transpose b is over here, that's some value. X transpose y star is over here as some value. and X transpose Y is maybe over here. So X transpose Y could be equal to X transpose Y star, but X transpose B always has to be greater than X transpose Y star. And therefore, X transpose Y star separates the two regions because all Y in this region is in C and all the other values are not in C. And this X transpose Y star value separates C from not C. And that is the separating hyperplane theorem. Pretty cool.